So once we have our nodes and switches wired together, you need to make sure that they can communicate. And this is done through what is referred to as the address layer of Ethernet communication. The address layer consists of multiple components: the MAC address, the IP address, a subnet mask, and a gateway address. And each of these have their own role in establishing their communication. In this chapter, we will discuss the address layer. In the last chapter, I mentioned that a switch learns the MAC addresses of each of the connected nodes to create a device table to allow communication. But what is a MAC address? A Media Access Control, or MAC address, is a unique identifier assigned to every node. MAC addresses are set permanently by the manufacturer and are stored in hardware's read-only memory. These cannot be changed by the end user. The address is a 6-octet hexadecimal number sequence, with the first 3 octets being assigned as a manufacturer's ID number, and the last 3 octets being left to the manufacturer to use as they wish. Now, here at ETC, we were assigned a manufacturer ID number of 00C016 by the IEEE. We used the last 3 octets to individually identify each of the network products that we manufacture. Next in the address layer is the Internet Protocol address, or IP address. The IP address is a unique identifier that is set for each node on a network. While no 2 nodes in a network will have the same IP address, many networks might use the same IP addressing scheme, and as long as they're not directly communicating, this is not going to ever be a problem. The IP address is a 4-octet binary numerical sequence, and addresses can be any number within that sequence between 1 and 254. The number 0 and the number 255 are reserved for special functions. An IP address serves 2 principal functions: network identification and node identification. The first 2 octets in the address are the network ID. These define the range of nodes that can talk to one another. ETC, for example, uses 10.101 as our network ID. These 2 octets define the overall scope of the network. The last 2 octets are the node's ID. This is a specific address for that node. ETC uses these last 2 octets to separate our nodes by product line. 101.1 for Paradigm, 50.1 for Obsession are 2 different examples of our addressing scheme. We do this so that we can keep all of our products on the network talking to each other, but use the same defined ranges so you can tell by looking at an IP table which product is which, and also to avoid any IP conflicts. Here's another way to think about IP addressing. Let's say you wanted to call me at ETC. First, you would call the main ETC phone number, 800-688-4116. This is like a network ID. Then, you'd need to get to my desk, so you'd request extension 5056. This is like a node ID. So now that we understand how the IP address layer works, how do you determine which nodes can communicate on a network? This is where the next component of the address layer comes in, the subnet mask. A subnetwork, or subnet for short, is a divisible subdivision of an IP network. The subnet mask determines which part of the IP address is used for a network ID and which part of that address is used for a node ID. A subnet mask is a 4-octet binary number combination, and while any numbers can be used, typically a subnet mask makes use of those special numbers, either 0 or 255. When 255 is used as part of a subnet address, it allows communication between nodes that share that portion of their IP address. If the octets in the IP address match, then the nodes can talk to each other. Otherwise, messages between them are ignored. When a 0 is used in a subnet mask, those octets of the IP address do not have to match for the nodes to be able to communicate. At ETC, we use a defined subnet mask of 255.255.0.0, and what this does is defines the network ID as the first 2 octets of the IP address, 10.101, while the remaining 2 octets become the node ID. With a subnet address of 255.255.0.0, any nodes whose IP addresses start with 10.101 can communicate, regardless of the last 2 numbers in their address. The last component of the address layer is the default gateway. This is the address that a switch will use if the message it is trying to deliver is to a node whose IP address does not match any of the nodes within its device table. This gateway address allows a node on one network to talk to a node on another network through a device called a network router. And while this method is rarely used with a standard lighting network, you still have to provide a default gateway address, as some network devices require this address in order to pass communications. Windows 7 is a perfect example of this. Typically, the default gateway is either 10.101.1.1, or the default matches the IP address of the node itself. Now, if a router is being used in the system, instead of a default gateway address, you would provide the IP address of the network router. Now, as we just mentioned, a network router is another special type of node that is designed to pass information from one IP network to another. Best practice is to place that router in between switches. Routers are typically used in large systems where you may have multiple networks, or large systems where you've separated your networks by floor, facility, or region, but still need to pass some level of command structure between them. By installing a router, you can direct node communication between devices, regardless of IP addressing or subnet masks. Here's an example of a fully addressed lighting network. Each device uses the same subnet address of 255.255.0.0 and the same default gateway of 10.101.1.1, so they can all communicate together. Then, each device has its own IP address with the same network ID using the first two octets of 10.101, which again allows them to communicate together. Now, the node ID is the last two sets of octets in the address, the third octet being used to determine product type. CEM, for example, is 101. Net3 nodes, for example, are 50. These are determining the product type. And the last octet is device specific. So a CEM, for example, might use that last octet to match its rack number. And this concludes our chapter on addressing.